Hey everyone, guess what time it is? It's time for part 2 of the 3D printed zinc carbon battery cells, because believe it or not, it's been almost a year now since I made part 1, and since then I have made some pretty major improvements to pretty much every single aspect of the battery cells, everything from the materials to, most importantly, the manufacturing process, where I've essentially created a miniature assembly line. So starting off with the first major improvement that's going to contribute to a lot better performance for the actual battery cell, which is the swapping of the ammonium chloride electrolyte and zinc chloride electrolyte for a proper alkaline potassium hydroxide electrolyte. So we are now officially moving on from zinc carbon batteries to alkaline batteries. And they are not only the most popular type of single-use batteries in the world, but the types that most people are the most familiar with. So they are what your Duracells and your Energizers and basically any 1.5 volt alkaline batteries are made of. So basically, I kept running into an issue when I was first making these cells where every time I would 3D print a piece, the dimensions would be slightly different in a way that I would have to go around with a razor blade all around here and sometimes on the joining piece itself to try and get them to fit snugly in such a way that part 1, the half cell 1, goes in much tighter than half cell 2. So that way when you put in the second piece, the first piece doesn't get popped out. So the way this works is that it's pretty simple. Each one of these joining pieces is labeled 1 or 2. If we take the joining piece for set M, we can see it says 1, and then you'll see that the first half goes in pretty tight. But if I go ahead and pop it out and then put in the second half cell for the cathode, you see it goes in much easier. So next, moving on to the most recent and in my opinion the most significant design improvement so far, which is the substitution of the very expensive pyrolytic graphite sheets, which look like this up close, for the much stronger, much more durable, reusable, and much cheaper solid graphite plates, which I've cut into strips wide enough to fit into the half cells, which I've actually modified the slot widths of to host the new thicker graphite. So by switching to the solid graphite, we end up with not only all of the benefits that I mentioned earlier, but we also end up with the added benefit of actually being able to directly connect our little terminal connectors to the graphite without fearing it ripping or tearing or anything because of how sturdy it is. So I've come up with a way to make the separators significantly faster than before, because before I used to have to go one by one, cutting the pieces of paper by eye, and then trying to get it to fit as perfectly as possible into these shells here. Taking advantage of the fact that in Photoshop you can set dimensions in millimeters and not pixels, and I basically just made my own little template here that I can print out, and then cut it into strips like this with an X-Acto knife, of course using a ruler. And then once all of the separators are cut out like that, I just go ahead and bundle them all up into a little stack like this, and then give it a quick staple. Let's see if it fits, and it does. So here I have gone ahead and wrapped up the separators in little post-it notes, both to protect them from contamination and to hold them together. So now let's move on to actually assembling the half cells. So let's go ahead and begin with one of each electrode and give them both a little alcohol swab. And after making sure both electrodes are relatively clean, it's time to start roughing up the surfaces using any sharp object. And the camera keeps going out of focus, but anyways, I like to start going at an angle, going nice and deep. I want to scrape and get underneath that layer in every single direction. So I go like this, like a checkerboard pattern, like that. And then I go and I do a final scrub, and then we're going to come right back once the entire graphite sheet is scrubbed up. Okay, so here is what it looks like after scrubbing it very thoroughly and then going over it with another alcohol swab. So you can see it's quite roughed up on the surface there, and I think that looks pretty good. So now let's move on to the zinc. Okay, and a few minutes of scrubbing later, here is what the zinc looks like. It looks a lot nicer than the other one because it's shiny, of course, but you can see it's the exact same pattern. You can see it's pretty scratched up. So now let's move on to actually inserting these permanently into these shells. So once again, let's go ahead and start off with the graphite side, and basically I'm just going to insert the graphite into the shell. We're not going to put any glue this time. I'm just going to simply put epoxy all around the outside edges here. Okay, and that seems to be the best I can do on camera, so I'm going to try and do the best I can off camera and show you what it looks like afterwards. And about 5 minutes later now, the epoxy is now fully cured because it's a 5-minute epoxy. So now we can go ahead and fill up each half cell with their respective materials. But right before doing that, there were a couple of people last time in my first video in part 1 who did want to know the weights of the individual pieces before and after I assembled them into the cell. So right before we do this, let's just go ahead and weigh out each of the components here real quick and fill it out in this chart here so that we can keep it as a reference as we keep iterating our design. Okay, so the first piece to weigh is going to be the half cell shell only. 1.00 grams. Next is the zinc electrode. Now this one is going to be like plus or minus 0.5 grams because I cut them to different lengths sometimes. So this one is 1.03 grams. Next is the graphite electrode. 1.09. Okay, and down to our last 3 items. So after that is going to be the zinc half cell shell and epoxy combination. 2.08 grams. Same thing after that, except with the graphite. 2.07 grams. So they almost weigh the same. And then lastly, our joining piece. So this is just the central piece that connects the 2 pieces together, and that is also 1.00 grams. Okay, so here is the completed chart, if any of you are interested, and I went ahead and added together the masses of the 2 half cell shells and the zinc, graphite, and of course the epoxy. So 2.08 plus 2.07 plus 1, so 5.15 grams before adding any separators or cathode mix or anything else. And with that, let's go ahead and fill up these things and activate them and turn them into a battery cell. So let's go ahead and start off with the zinc this time because it is less messy to prepare. So first what I'm going to do is actually insert it into the half piece joining cell. So looking for the side with the 1 dots on it to match up with the 1 on the back of the zinc. And then I'm simply just going to align the holes and then insert it into the shell. Basically at this point what I'm going to do is get this in as evenly as possible. Just like that, that's close enough for now. We're going to get it more perfect near the end. So now let's go ahead and start putting in our separators. So I'm going to start off by placing 2 sheets of the separators that we cut earlier on top of the actual zinc metal itself, followed by enough of these absorbent separators to get them to reach all the way up to the half circles. So just simply putting in one of these, and that's just going to cover the entire half cell shell, just like that. And I promise the results are all going to be worth it because the amount of current we're going to get is going to be insane. So now we can move on to the cathode. Okay, so for this step, I'm going to be doing it the way I should have done the first time, which is by actually compressing the cathode mix. So I'm going to be doing that using this C-clamp here and this little 3D printed block that I made that fits into the half cell that lets me compress the powder with the C-clamp. Okay, so once I've gone on a relatively even layer, I'm going to go ahead and take my little block here and very evenly and gently place it down, making sure not to go at an angle. And this is just to hold the powder in place as we transfer it over to the C-clamp. So I'm going to continue holding the assembly like this as I open this up, put it in and center it, and then simply just twist. Down like that, undo it, and then go back down again, just to give it some good compression. And I do this 3 times. After that, I'm gonna open it back up, take it out, and let's see what we've got. Okay. Nice. A nice compressed, basically like a pill of our cathode mix. So we're starting off with 3 sheets of the separators that we cut out earlier, the paper separators. Being careful not to disturb the compressed powder. And then just like with the zinc, we're going to follow up with some sponge separators is what I call them, the absorbent ones, right on top of that paper there. And finally, with all of that now in place, it's time to put both halves together. So let's see if all of this will go to waste, because I'm always scared that I'm gonna mess up something I spent so much time on. So putting the assembly that we made earlier on top of this little jig thing here. And I still haven't perfected it yet, so I do have to put a piece of a credit card there to prevent that side from going down, but I'll fix that quite soon. So because I couldn't find my glue stick, I'm gonna have to be careful when putting this down, because I don't want these separators and stuff to fall out. So what I might do is actually just hold it and put them together in midair. In 3, 2, 1. Not squishing. Putting it back on the jig, or even on the table here. And then I'm going to slowly orient it. Gotta use my tweezers here to keep everything in focus. And then push everything in place once I feel like it's even. Just like that. So it's almost finished now. It's not fully encapsulated. We still need to put it back in the C-clamp just to get it pushed past the parts where we put the epoxy, but it's pretty much finished. The only things left is to seal the sides so the electrolyte doesn't evaporate or leak out, and we'll be ready for testing. So I'm gonna go ahead off camera and seal this on the edges, let it dry, and then we're gonna test this thing out and see just how much power an alkaline electrolyte can give. Okay, so here it is after sealing it with the epoxy. Now, it was 5-minute epoxy, so I didn't have the longest time to work with it, so near the end here it did get kind of sloppy, but I got the job done. I got everything sealed so that hopefully nothing leaks out. So now let's go ahead and add the electrolyte into the fill holes and see how much better this performs compared to our older battery cells. Okay, time to test the cell. So for our electrolyte today, it's going to be a 30% solution by weight of potassium hydroxide, along with about 0.2 millimeters of this Kodak Photo Flow wetting agent, just to help everything absorb a little bit better and faster inside of the cell there. So the way I'm going to be filling this thing up, considering the caustic nature of the electrolyte, 30% potassium hydroxide is no joke. I'm going to be basically having the cell inside of this plastic bag here, and then I'm going to put the electrolyte in this little printer ink refill syringe thing, and then put the needle of it inside of this paper, if I can get that camera to focus on there, into that paper tube, which I'm going to then route inside of this paper, inside of this plastic bag, and into the middle hole there, and put enough electrolytes to fill the cell. Now, I won't be able to focus or zoom in and out as much because I don't want to touch my screen when my fingers are contaminated with the potassium hydroxide. Okay, so that paper tube thing, it wasn't necessary. I kind of popped it out, but I couldn't get it out of the bag, but that's fine. What I'm trying to do here is get that needle right to the middle hole there, just like that. So I'm going to start pushing on the syringe in 3, 2, 1. So the syringe is now down to 2.8 milliliters, down from 4 milliliters. Okay, so I've got the cell filled up and we had a little bit of overflow, which is fine. I'm just going to snip the top off and take the cell out and then wipe everything off. Okay, so with our battery now activated and with the holes now covered with some silicone to prevent the electrolyte from evaporating, let's go ahead and connect some multimeters, connect some loads. I made a second one of these that I've also activated, so let's connect them in a parallel and or a series. Let's do some actual fun stuff with these. Okay, so let's go ahead and connect these two cells to the multimeters, starting off with the one that we just made so that we can see how many volts we have. So one of these and one of those, like that, and the negative lead. Let me put it on the side, like that. Okay, so connecting the voltmeter, negative and positive. So 1.518 volts, so not as high of a voltage as I would want, but I know that it's not the chemistry because I made a tiny test cell beforehand and it gave me 1.7 something volts, along with an amount of currents that I don't want to spoil for you guys because that was insane. But I think that the reason that the voltage is lower here is because of either a combination of the photo flow that I added to the electrolyte, diluting it a tiny bit, and or most likely the increased amount of separators on the inside of this cell, because the test cell that I made had very few separators on it. But anyways, let's go ahead and check the voltage on the other cell too. Okay, so here's our second cell connecting negative and positive. So 1.537, not too far off the other one. So now that we know the voltage on both of the cells, let's go ahead and do some current tests on them. Not too high, because I do want to then connect these in series and see if we can power some stuff with it. But first, because I do kind of feel bad because we were kind of supposed to get a much higher voltage, I've gone ahead and made another test cell that I was talking about, and I've also made another batch of electrolytes, this time at 35%, because that is what I found in a Duracell data sheet. So hopefully this cell does better. So let's go ahead and activate this. Okay, just under a milliliter of the electrolytes is in the pipette. I'm gonna start off with 1 drop because we need to get the paper to start wicking the electrolytes in. And as soon as it does, we should see the voltage start to climb. There we go. That was almost instantaneous. Okay, I'm gonna leave it at that and let it soak it up. Okay, so the voltage stopped going down and now it's going back up. It's pretty interesting, actually. Okay, so about 2 minutes have passed so far and we're already up to 1.56 volts. So I'm waiting for it to go to at least 1.6 before we begin discharging. So we've reached 1.61 volts and it looks like the electrolyte has pretty much all been soaked up, but I'm not sure whether or not I want to add a little bit more or just let it stay as is. But since the voltage seems to be going back down and we still haven't reached what I reached last time, I'm going to add a tiny bit more. Okay, so I'm not going to touch the separator, I'm just going to put it on the graphite. Okay, that seems to be helping. I just don't want to go too much with it. Okay, so I've got it to be relatively stable around 1.56 volts. No matter how much more electrolyte I add, it just stays around 1.56 volts. So I'm just going to go ahead with the ammeter here and begin doing our discharge test, starting off with a 220 ohm resistor. So I'm going to tap the resistor on the terminal here in 3, 2, 1. 6.77 milliamps. The voltage is still going down quite fast, so I don't think it's soaked all the way through yet. Okay, so dropping it down to 100 ohms in 3, 2, 1, 14.6 milliamps. Again, the current just keeps going down. Voltage is going down kind of fast too. So at this point, I have a feeling that it might just be the cathode mix. My scale isn't the most accurate when it comes to weighing out smaller quantities. I only made like 2 grams of cathode mix, which meant like only 0.5 grams of carbon black. So it may have resulted in a mixture that has more carbon than it should, meaning less of the actual active manganese dioxide. So I'm just going to do a quick short circuit test here, just to show you guys the amount of current that this thing can produce, if it ends up being able to produce it with the cell. So in 3, 2, 1. And oh my god, this multimeter, it cannot register the current properly. I am so sorry about that. Let's go to 10 amp mode, because my other multimeter is limited to 200 milliamps, and that's going to easily go over 200 milliamps. So in 3, 2, 1. Oh my god, I just reviewed the footage. I went over it frame by frame to see how much current we got, because this multimeter has kind of a slow, whatever rate it's called, the counts, whatever the things are, 6,000 counts. And it was, do you know what the peak was? 702 milliamps. That's over half an amp. Last time, with my test cell that I was talking about that I didn't show on camera, I got like 300 milliamps. This just almost made an amp. That is insane. And it dropped down to, and it was still above 0.2 volts, making 700 milliamps. And then it like went down to like 645 milliamps, and I'm going to show you all of those like screenshots or whatever on screen. Okay, back up to 1.4 volts, and I've got 4.7 ohms on the resistor. In 3, oh, let me switch to amp mode. In 3, 2, 1. 210 milliamps, very nice, very nice. I didn't see the voltage on screen there, but I think it was over a volt. Let's chop that in half. So 4.7 ohms divided by 2 this time in 3, 2, 1. 340 milliamps. That is excellent given how tiny this cell is. So I want to keep going with the video, so let's just drain this thing in 3, 2, 1. Look at that. 240 milliamps, and we've just dropped to the voltage where the cell would be dead. So I'm going to disconnect it. I think you guys get the point. I'm sorry that I couldn't show the higher voltage, but you can definitely see the effect of the alkaline electrolyte on the amount of current that I can give and how well it can bounce back its voltage. So with that, let's continue on with the video. Okay, so starting right off with a 100 ohm resistor for our discharge test. So voltage is on this multimeter, current is on that multimeter. Tapping the lead in 3, 2, 1, 14.5 milliamps. Looking decent, okay. I wish the voltage was going down a bit slower, but seems fine. So now let's step the resistance down to 50 ohms. Tapping the lead in 3, 2, 1, 27.9 milliamps, 1.4. Once it gets to 1.400, I'm going to disconnect. Okay, so the performance seems acceptable. So I'm going to do the exact same thing to the other cell so that we don't have an unequal amount of discharging on the cells. And then we're going to connect them in series and power some LEDs with it. Try and power some like small low power circuits with it. And then I'm going to connect it to my Datalogger, which I finally got working, and log the discharge data with a given resistance. Okay, so to put these in series, I still haven't come up with a proper system yet, but I think if I just put these on top of each other like that, and then connect the positive and negatives on this side, we should have these two in series coming out from this side. Okay, so basically what I did was use some double-sided tape to put these two together. So all I need to do now to put them in series is to tie these two wires together. Okay, so connecting them in 3, 2, 1, and there we go, 3.00 volts. Okay, so I've gone ahead and put an LED with a 220 ohm resistor on a breadboard here. So I'm gonna go and connect these leads to some jumper cables and power the LED and see how brightly it turns on. Okay, ready? In 3, 2, 1. Let's see the voltage on screen here, 2.98. It's not really in focus there. Let me turn down the light so you can see this a bit better. Okay, take 2 with the lights off. That is, I'm not gonna lie, that is pretty bright. And I think this breadboard isn't too good. Let me put this right on the, let me put it right next to that point right there. Yeah, that is that's a pretty bright glow right there. Let me see if I can find a step-up module, maybe a better breadboard, because this thing is really flickering. But if we take a look at the voltage on the multimeter here, 2.962 volts, 2.96 volts, which is not bad. So I think I'm gonna go ahead and disconnect this and try out a different load. Okay, so I tried hooking up one of these step-up modules to try and step the 3 volts up to 5 volts so I could power like an Arduino or something, but it didn't seem to want to hold like a stable voltage. It just kept fluctuating up and down between like 5 and 7 volts, like continuously going up and down. So instead, what I'm gonna do is use my Datalogger here, which I finally got working, which basically records the milliamps, the real-time using a real-time clock chip, the load voltage, the wattage, all the stuff like that onto a micro SD card, which I can then turn into a graph using Microsoft Excel. Okay, so the first thing I want to power with this is this tiny little DC motor. So I'm just going to hook up the ammeter leads to it. And then I'm going to power on the motor by simply touching the VN minus lead on my little Datalogger here to the positive lead of the motor. Ready? In 3, 2, 1, go. When it gets to 2.4 volts, I'm going to disconnect it. So that was pretty decent. Like, it was holding a pretty good voltage while giving a pretty good amount of current. So let me go ahead and find a bigger motor. Okay, I've got a slightly bigger motor here now. So let's try this one out. 3, 2, 1. Oops. Oh my god, why is it? There we go. You guys probably can't see that. Yeah, not bad at all, not bad at all. That's it's maintaining the current pretty stably. Yeah, that's pretty good performance. So now let's switch over to some resistors. Or actually, you know what? I've changed my mind. What I'm going to do is basically do a very quick tap to here just to see what the short circuit current is. And then after that, I'm going to leave this plugged in to the Datalogger with like a 50 ohm or like a 45 ohm resistor and just leave it until it runs completely flat and then turn the data into like a graph or something. Because I really don't think it would be too entertaining to watch me connect different resistors to this, especially considering how we didn't get the full 1.7 volts per cell. So I'm just going to do the quick tap to the thing here for a short circuit current test in 3, 2, 1. Oh my god, that went over 200 milliamps. Okay, let's flip this over. We are now in amp mode. Ready? In 3, 2, 1. 0.1 amps. That's not telling me anything. Okay, let me go and get a better multimeter. The short circuit current doesn't seem to be showing up too well on the multimeters here. It might be because of the Datalogger. So let me just connect the Datalogger directly to the battery terminal. Okay, so shorting the Datalogger with the battery cell attached. So this is going to be shorting the battery cell and then logging the current and everything onto the SD card. In 3, 2, 1. That should be enough. Let me do another one. There we go. So now I'm just going to connect a resistor to this, leave it connected, and just let it run until the battery is dead, and then just turn all of the data on the SD card into a graph. Hey everyone, so I'm currently editing the video and I had gotten to the point where I went to get the SD card out of the Datalogger to make the graph in Excel, and unfortunately it seems like the data on the SD card, everything got corrupted. I did have a record before I began recording this video, so I didn't lose my other data, but everything that we recorded onto it today is gone. And I tried multiple softwares to try and get the info back, but it seems like it's just completely corrupted. And the reason I think is because the battery pack that's connected to the Datalogger for actually powering it basically dropped below the 5.5 volt mark, and that basically led to unstable voltage for the circuit that I think is what caused the corruption on the SD card. And the reason I think this is the case is because on my Datalogger I have two LEDs that I've coded in, the green one and a red one, and the way that it's coded is that if there's any issue during the writing process to the micro SD card, so right over here, then the red LED is going to come on and the green LED will not flash. The green LED is only coded to flash if and only if the entire process for opening and writing to and then closing the SD card has been successful. So you can see that it's flashing green here, meaning that it is writing data to the SD card. And in the several weeks that I've actually been using this Datalogger for my own purposes, I have never had the red LED come on once. However, during the discharge that I was doing when making this video for testing the cells, they did come on, and right around when the battery pack went below that 5.5 volt mark. And why is there a piece of wood on my breadboard? But anyways, for the missing data, here's what I'm going to do. I'm going to keep working on improving the battery cells and making the Datalogger more advanced. Probably making it into a PCB at some point, so that in part 3 we can spend more time on actually testing out the cells, powering different stuff, rather than actually making them. And what I'll do to make sure the same thing doesn't happen again is just have the data ready before I even start recording. So hopefully this wasn't too much of a letdown. Again, I'm sorry about the corrupted data, but it just took a really long time to make those battery cells, and I really do think we're going to get better results anyways in part 3, so I really do hope that that wasn't too big of a letdown. But I did finish the chart for anyone who's interested, so you can take a look at this if you're interested. I'll focus on it here and get a better view. And I guess this is the end of the video, so if you liked it, please do leave a like and or subscribe, and I guess I'm going to see you in the next one.